All right, so in this section we're going to be talking about the most important theorem in all of calculus, and that is given the name Fundamental Theorem of Calculus, or FTC for short. And so what we're going to do is we're going to explore this fundamental theorem of calculus through some inductive reasoning, which means looking at some patterns and seeing if we can come to some conclusions based upon those patterns. So in this first set of problems, we're going to do two steps. We're going to first of all determine what capital F of x is as a function of x. Remember, capital F is your antiderivative, and so we're going to be determining what our antiderivative is in terms of x. And then our second step is to determine what f prime of x is going to equal. All right, so if we do that on our first problem here, we're going to get step 1, which is t cubed over 3, and then we evaluate this between 0 and x. So what we've talked about before with definite integrals as far as evaluating, you substitute in your upper bound, which is going to give you x cubed over 3, and then you subtract, and then you put in your lower bound, which is 0. And so what you end up with is going to be x cubed over 3. All right, so step 2 says to now take the derivative of this. All right, so on the derivative, when we bring this exponent to the front, that's actually going to cancel with our denominator, leaving us with x squared as our derivative. So f prime is equal to x squared. All right, so the next one, we're going to find the antiderivative, which once again is going to be t cubed over 3 plus, and this one would be 4t squared over 2, which simplifies to 2t squared, evaluated between 1 and x. So substituting x in, you're going to get x cubed over 3 plus 2x squared minus, and then 1/3 plus 2. And then our derivative of that answer is going to be x squared plus 4x, and then the derivative of this, that's a constant, so that just is going to be 0. All right, so let's look at the next one. Square root of t can be written as t raised to the 1/2 power, so the antiderivative will be t to the 3/2 over 3/2, which is the same thing as 2t to the 3/2 over 3, evaluated between 5 and x. So we're going to get 2x to the 3/2 over 3 minus 2 times 5 to the 3/2 over 3. And our next step is to find the derivative of that. Well, the derivative of this part, when you bring the 3/2 to the front, cancels with the 2/3, so you're just going to get x raised to the 1/2 power. And then this is a constant, so the derivative of that is 0. And one more here. The antiderivative of sine is negative cosine of t. Evaluated between 1 and x will give us negative cosine of x minus negative cosine of 1. And then f prime, well, the derivative of cosine is negative sine. We already got the negative in front, so that turns it back into a positive sine of x. and then this is a constant, so its derivative is 0. So let's look at our patterns here. This is what we started with for our function, and this is what we ended with for the derivative. This is our original function. This is our derivative. Original function, derivative. Original function, derivative. So hopefully it's not too difficult to see that all that we are doing is when you have a capital F, which represents your antiderivative. So when we find f prime, that means we are finding the derivative of the antiderivative from 0 or 1 or 5. What we're doing is going from a constant up to x. And so let's look at this one right here. If capital F of x is equal to this integral from a constant to x, then all we have to do is substitute x in place of t to find f prime. So that would be x to the 7th power. This one would be square root of 4 minus x squared. It's pretty easy. And so putting this in a notation, if we take the derivative, which means d dx, the derivative of this integral, which again means the derivative of an antiderivative, all you are going to get is the original function in terms of x. All right, so now we're going to look at the next pattern here. And instead of x, we're going to have x squared on these. Still going from a constant up to your variable. Same two steps. So the first step here is going to give you t cubed over 3, evaluated between 0 and x squared, which will give you x to the 6th power over 3. And then we take the derivative, and the derivative is going to give you 2x raised to the 5th power. So the thing is, this is not quite like the other one. We cannot just substitute x squared into t and get our answer. That would end up being x to the 4th. That is not what our answer is. So what I'm going to do is I'm going to actually split this up a little bit and say this is equal to 2x times x squared raised to the 2nd power. All right. So what's happening is this x squared is going in place of the t. That gives us this x squared here, and then raised to the 2nd power, because t is raised to the 2nd power. Well, where does this 2x come from? Well, think about this right here. The derivative of x squared is 2x. So is that a coincidence, or is that going to be a pattern? Well, let's find out. Let's do a couple more of these here. All right, so on the next one, if we take the antiderivative, it's going to give you t cubed over 3 plus 2t squared, evaluated between 1 and x squared. Substitute x squared in, you're going to get x to the 6th power over 3 plus 2x to the 4th power and then minus, and then plug in the 1. All right, so let's take our derivative now. The derivative, well, the derivative of x cubed over 3, we established, is 2x to the 5th power. And the derivative of 2x to the 4th is 8x cubed. All right, so let's once again break this up a little bit. And let's say that we've got a 2x that we can factor out of this problem. Well, that would leave you with x to the fourth, and x to the fourth could be written as x squared squared. 2x factored out of this will be 4x squared. And you can see how this relates back to our problem originally. If you take the x squared, put it in place of t right here, that would give you our 4x squared. Put x squared in place of t right here, that will give you x squared squared. And then we have this 2x, just like we had on the first one, and that 2x is our derivative of this right here. All right, so let's try one more here. Remember, we said this one is t raised to the 1/2, so the antiderivative was 2t to the 3/2 over 3, evaluated between 3 and x squared. So that's going to give you 2x to the 3rd power over 3 minus, and then plug in the 3, we don't really need to worry about the constant too much, because when you take the derivative, the constant is going to go to 0. All right, so now the derivative of this first term, if you bring the 3 to the front, that will cancel with our denominator, leaving you with 2x squared. Well, 2x squared could be also written as 2x times x. And this x could also be written as 2x times the square root of x squared. So you can see what's happening here. You've got your derivative of the upper limit of integration here, and we're substituting x squared in place of t, which gives us the square root of x squared term right here. All right, so we can kind of bypass a few steps here, and we can say our derivative, well, we would take the derivative of x squared, which is our upper limit, which is 2x, and then we would multiply that by sine of x squared. That would be our derivative of this integral. The next one would be 2x times cosine of x squared, and the next one is 2x times the square root of 9 minus x to the 4th power. Notice it does not matter what our lower limit of integration is, because that lower limit of integration creates the constant that was on the end of our term, and then when you take the derivative, that part goes away. It turns to 0. So let's think about a rule that we can apply now. And so the rule on this would be the derivative from a constant up to x squared of f of t. That's going to give you the derivative of x squared, which is 2x, times the function evaluated at x squared, which simply means put x squared into your function. Now, an even more generic term, because these were with x squared, this upper limit could be any function in terms of x. So if it's any function in terms of x, then a generic formula would be g prime of x, so the derivative of that upper limit, times f of g of x. All right, what I want you to do now is go ahead and pause this video for a minute, and I want you to try to answer these questions, numbers 13 through 22, as quickly as you can. and then unpause the video and check your answers. So real quick, just go ahead and pause the video right now. Okay, you can go ahead and check your answers according to what we have here. Over on the right side, numbers 18 through 22, I did simplify my answers to these right here. All right, so let's take a look at a few problems now that we can work related to this. The first problem, number 24, says what is h prime of x if h of x is this integral? Well, h prime would simply equal f of x. And that's all that we need to put onto this. So now the next one says determine the x-coordinate of the relative maximum and minimum of h of x and justify our answer. Well, if you think about relative maximums and minimums, that is where your derivative changes sign. For a maximum, your derivative changes from positive to negative. For a minimum, your derivative changes from negative to positive. The derivative of h, because that's what we're looking for, is the maximum and minimum of h. So we need to look at h prime. H prime, however, is equal to f. And this is the graph of f. So we are looking for the relative maximum and minimum, which is where h prime, which equals f, changes sign. So you are going to have a relative max at x equals 6 because h prime, which equals f, changes from positive to negative. And then you're going to have a relative min at x equals 0 because h prime, which is f, changes from negative to positive. All right, so the next question says determine the maximum value of h of x on 0 to 10. All right, so maximum value, what we're going to do then is going to fill in our table over here. And so on this table, let's go ahead and fill in some values. H of negative 1, which is what we're looking for right here. H of negative 1, come back to our integral. H of negative 1 would equal the integral from negative 1 to negative 1, which is going to be 0. So the next one would be h of 0. Well, h of 0 would be the integral from negative 1 to 0. And negative 1 to 0, if you come over here, that would be the area that is right here. And that area is negative 1. All right, so the next one is h of 1, which will be the integral from negative 1 to positive 1. Well, the integral from negative 1 to positive 1 would be those two areas combined. Well, this is a negative 1, this is a positive 1, which means those two areas cancel out, giving you an area of 0. All right, now the next one would be h of 2, so that means the integral from negative 1 to 2. So that really means 0 plus these two extra boxes. So that's going to be 2. And then for 3, we add 2 more boxes, so that's 4. Then we add 2 more boxes, 6. Then we add 1.5 boxes, so that's going to give us 7.5. Then we add another half, puts us at 8. All right, so now the next one we're going to be subtracting, so we're going to have this area down here, subtracting a half will give us back down to 7.5. All right, then we're subtracting 1.5 boxes, which puts us back down at 6. All right, and then subtracting another 1.5 is going to go down to 4.5, and then subtract a half, put us back at 4. All right, so determining the maximum value of h of x on this interval, that maximum value is going to be at x equals 6, and the max value is 8. So to answer the question, this is the maximum value, 8. All right, so then the next one, determine the minimum value. The minimum value is just smallest value, which is -1. And this occurs at x equals 0. All right, let's look at the next problem here. If g of x is equal to this integral, and we want to find g prime of 2, the first thing that we are going to need to do is find g prime of x. So g prime of x would be the derivative of this integral, which is our fundamental theorem, which tells us all we have to do is substitute x into our problem here. And then we can evaluate this integral at 2, so that's going to give us 1 over 1 plus 2 cubed, which will be 1/9. Now, if you'll notice, on this problem, your variable is in the lower limit of integration and the constant is up top. We need to switch these two things. So we can switch these two things if we put a negative in front of this integral. So this would be equivalent to this. And now we can find the derivative, which will be negative. Now we need to take the derivative of this, which will be 1/2 x to the -1/2. And then we can plug that x to the 1/2 into t. And a simplified version of this would be negative sine square root of x over 2 square root of x. All right, next problem. The difference here is we have variables in both positions. Now, what we're going to do is apply this property where the integral from a to b plus the integral from b to c is equal to the integral from a to c. And so what we can do is we can break this up into two integrals. If you have x squared and you have x cubed, those are two functions that we are integrating between, or two x values. There is going to be a constant somewhere in between those two values. So we can actually rewrite this integral as the integral from x squared to some constant that is in between x squared and x cubed, plus the integral from that constant to x cubed. So whenever you're integrating between two variables like this, this is what you want to do, is split it up with a constant in between those two variables. Now this first integral, what we're going to do is switch the order of these things. So this becomes a negative integral from the constant up to x squared. And this other integral we can keep just the same. And now we can evaluate by plugging x squared in. And we multiply by the derivative of x squared, which will give you 2x. Plugging x squared into t is going to give us x to the 8th in our denominator. And then over here, the derivative of x cubed is 3x squared over 2 plus x cubed raised to the 4th power is x to the 12th power. All right, so this next one, just kind of read through this. We have a graph that is given to us. This is going to be the graph of f. So the graph of the function f consists of 3 line segments. If the function g is an antiderivative of f such that g of 2 is equal to 5, for how many values of c, where c is between 0 and 6, does g of c equal to 3? All right, so the first thing that I want to do with this is we need to bring this into our problem somehow, keeping in mind that g is our antiderivative. So if we take the integral of f, and let's just say between 0 and 2, the integral of f means find the antiderivative. Well, the antiderivative is g. And we're going to be evaluating g from 0 to 2, which means you find g of 2, and then you are going to subtract g of 0. All right, so this gives us an equation, and this is what you are going to be often looking at, where your integral equals the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. That's all this says. This is your fundamental theorem of calculus. Well, this integral, we can find the value of this. The integral from 0 to 2 just simply means this area of this triangle right here. Well, the area of that triangle is 2. Well, g of 2, what value was given to us right here, g of 2 is 5. So we can put 5 in here. Minus g of 0, which we can now solve and get g of 0 is equal to 3. All right, so let's think about this for a minute. G of 0 means that's the value that we are starting with, which is 3. If we're starting at 3, g is the antiderivative, which gives us the area. All right, so from here to here, that would be 3 plus this area. Well, 3 plus 2 is 5. That's what this is right here. Okay? So this says how many values of c does g of c equal 3? Well, here's 1 right here. We know g of 0 is equal to 3. So that's 1. Well, if you're starting with 3 and you add 2 right here, well, if you keep going, you're going to be subtracting 2 right there. So you're going to be subtracting 2 right here. So if you start with 3 and then add 2 and subtract 2, that's going to put you back at 3 again. So that means g of 4 would equal 3 also. Well, now we're subtracting another half. I'm sorry, not a half. We're subtracting 1. Well, if we subtract 1, somewhere between here and here, we would be adding 1 because the area is going to be 1 somewhere in between here. And so we know g of something is also going to be 3 over here as well, because it will counterbalance this negative 1 right here. So that means that there are actually 3 places or 3 values of c where g of c is equal to 3. All right, and the next one, let h be the function defined by this integral from pi over 4 to x. Which of the following is an equation for the line tangent to the graph of h at the point where x equals pi over 4? Now, in order to get the equation of a tangent line, you need 2 things. You need a point on the function, and you need the slope or derivative of that function. All right, so the point, we know the x value is pi over 4. So if you take this pi over 4 and I want to find the graph of h, the tangent line to h, that means I need to find h of pi over 4. Well, that would be the integral from pi over 4 to pi over 4, which is 0. That was easy. And then we also need to know h prime. Well, h prime of x is going to equal sine squared of x. That's our fundamental theorem. If we want to now evaluate at pi over 4, we're going to find the sine of pi over 4 and then square that value. Well, that's root 2 over 2. Squared is going to give you 2/4, which is a half. So we can now fill into the equation of our tangent line where the y value is 0. M is your slope, which is your derivative. That's 1/2. X minus the x value, which is pi over 4. And y minus 0 is just y. So that gives us 1/2 parentheses x minus pi over 4. All right, this one's similar to that. The derivative of the function f is continuous on the closed interval. Values of f and f prime selected values are given in the table above. If this integral of f prime is equal to 8, then what's f of 4 equal to? Well, keep in mind we're taking the integral of a derivative, which is the same thing as taking the derivative of an integral, basically. So remember that the antiderivative of a derivative is just going to give you the original function, f. So that means if we write this out, the integral from 0 to 4 of f prime, that would equal just f evaluated between 0 and 4, which means f of 4 minus f of 0. We can plug some values in. We know this is 8. That was given to us. F of 4 we don't know because that's what we're looking for. We'll leave that as f of 4. Well, f of 0 we can get from our table up here. F of 0 is 5. So adding 5 over to the other side gives us f of 4 is equal to 13. And another tangent line problem. Which of the following is our equation of tangent line? And this is our function, or what y equals right here, 3 minus this integral, at the point where x equals -1. So we need a point and we need a slope. So the point is -1, and you would plug -1 into our function. Well, that would give you the integral from -1 to -1, which is 0, leaving you with 3 minus 0, which is 3. So that's the coordinate of our point. And now we need to know what the slope is. Well, the slope would be y prime. Now the derivative of 3 is going to go to 0. And then this derivative of the integral is negative, because you have a negative out in front of the integral, e raised to the negative x cubed. And we are going to evaluate this derivative at -1, which means negative e to the -1, -1 cubed. All right, so let's simplify this. -1 cubed is -1, but this turns it into a +1, which means this is equal to just negative e. All right, we can write our equation, the tangent line now, which is y minus 3 equals your slope, negative e, times x minus the -1, which makes it +1. And that ends up being this answer right here.